and this is a theory. When we have a theory, like what evidence do you have to support that particular theory? And so for Dalton, what was his evidence that he had to support the theory?
There was the constant properties.
You should.
Constant properties and chemical conversions.
You should.
Conservation of energy.
This should be quick. I mean, because you don't want to, like, if you have a test, you don't want to waste a lot of time on the simple problems, the recall problems, because you need time to focus on the challenge problems. And so if you're spending a lot of time, what was that? Unfortunately, that's going to eat up time that you'd rather spend on thinking about things that are covered. So it would be good to recall. I mean, something like this should be quick. What was the evidence?
Constant composition and chemical conservation.
Yeah, law of constant composition and
Law of
the
chemical
proportion.
law of multiple proportions was the
the other
prediction.
one.
Yeah, it was
And
chemical
that also
conservation.
helps support, because the theories, good theories you should be able to make predictions with those, right?
Constant composition and conservation.
And conservation of mass. So you want, recall information. How do you get that? Because the tests are a combination of recall and a challenge. And recall, how do you get recall? Good recall?
By reading the material.
And
every
over and
single
over and
day.
over and over again.
Memorization.
Repetition.
Yeah.
I mean, it's like
Or law of repetition.
you just do a lot of repetition and then you'll get it. It's like memorizing the ions. But you don't want to have to do everything by memorization, do you? No, so there are certain things. We'll talk about the atomic force microscope in a second, but if you memorize the eights, right, what else can you get from the eights? Well, you can get the ites, right? You can get the,
Eight.
you don't get the,
Ite with an IDE.
I feel like we already know the eyes.
Take acid.
Yeah, you can
you
get
could get the per eights, you could get the hypo
Eight.
ites,
Or that.
and then you could get the acid anions, like the bi and the hydrogen.
Those are the same thing, right? Just
Yeah,
different.
those
Okay.
are the same thing. What else can you get from this? What else you can get from this are the, maybe I'll put it over here. Have you ever heard of the thio? This is going to be a new one. Thio, we don't have to memorize these either, because the most common thio is thiosulfate. Thio means substitute S for O. And so, what is sulfate? Sulfate is SO4 2 minus. And so all we do is we remove one oxygen and replace it with a sulfur. They're in the same family. And so we end up with S2O3 2 minus. Rather than having 4 oxygens, 1 is lost, therefore we have 3, and then 1 extra sulfur is gained. So this is thiosulfate. And that's pretty much the most important. I mean, we could have thiosulfite too, or other thio type. But these don't have to be memorized. I don't make flashcards for this. You just know that. So we try to minimize it and not have to memorize everything, but that was the evidence. Nowadays, the evidence for atoms is just overwhelming. You have atomic force microscopes, you have scanning electron microscopes, you have scanning tunneling microscopes. You have lots of different microscopes that can just probe the surface. And then you could see the atoms, and you can actually manipulate the atoms. There is the IBM boy. Have you seen the IBM boy?
Stop motion animation with just atoms.
Yeah, they've made all kinds of figures using single atoms. So these are single atoms, and if you try to take the single atoms and then break them into smaller things, then you don't. Yeah, this is all made of atoms too. They have to get these really cold, otherwise the atoms are vibrating. And so this is very cold. So they made the world's smallest movie made of single atoms. So nowadays, there's no question. I mean, people can manipulate atoms. They can visualize the atoms using these microscopes, not optical microscopes, but all these other microscopes. And they can visualize these atoms in X-rays. You know, usually what people want is they want an X-ray, let's just say X-ray structure. We try to get single crystal X-ray structures of things. And so what you do is you get X-rays, and the X-rays will scatter off the electrons in the atoms, and then you can regenerate images. So this is just a ball and stick image, but the positions, you know, where the atoms are located, those were actually measured using X-rays. So the X-rays will give you a three-dimensional picture of the molecule in this case here. And so this is what we call single crystal X-ray structure. And X-ray structures are very useful, but again, these are solids. They have to be solids, so the atoms don't move too much. And the atoms do move a little bit. And so when you look at these, the atoms don't look perfectly spherical. You see that? The atoms have a little oblong shape to them, and the oblong shape is due to the vibrations. The hydrogens are difficult to detect because the hydrogens only have one electron, and so they're pretty invisible to X-rays. People who want to really map out the hydrogens don't map it with X-rays, they map it with neutrons. So they use something called neutron diffraction to pinpoint the hydrogens. But since hydrogen is such a simple atom, these are just put in place by calculation. And so we can just fill in the rest of the structure. But this is a single crystal X-ray structure. So nowadays there's just overwhelming evidence. So they're pretty much, pretty much everybody believes in atoms. Because, to not believe. But back in Dalton's times, it was a bigger sell, that is, you know, to try to convince people of the existence of atoms. You know, and this is part of the scientific, this is why they say, you know, the science, you know, modern science began around Le Chatelier's, because Le Chatelier's based things on observation, right? And so law of conservation of mass, that was based on observation. Before Le Chatelier, it wasn't really, it was a mix of magic and science, you know. And before Le Chatelier's, they didn't call them chemists, they called them alchemists. And alchemists had a bit of magic in there as well.
I love this study of alchemy. It's so funny.
What's that?
I said I love this study of alchemy. It's really funny.
Yeah.
You get some really weird territories.
Is alchemy like proto-science?
Yeah, proto-science, right. The alchemy, you know, the big goals of alchemists were to
Turn lead into gold.
turn lead into gold, the
And-
philosopher's stone.
And the philosopher's stone, yeah.
The elixir of life and philosopher's
I know
stone.
they were trying to find the elixir of life.
But, you know, if you hypothesize that, what you know, evidence do you have to support that? You know, and maybe there were evidence of chemical changes.
Chemicals together
Yeah.
like we were yesterday.
Yeah, right. And so there's evidence of chemical changes, and then, you know, if you're going to devote your life to finding these things, you know, is that enough to go off? You know, to do it.
What interests me is like, where do they get the funding? The first houses. It was like
The early-
chemicals wanting to live longer, right? They're just like,
Yeah,
Probably, yeah.
yeah,
Especially
definitely.
if they were trying to find like the
Right.
elixir of life.
Right, but you know, if you want some interesting reading, there's this. Have you heard of this this book? I think. Oops, that's not.
I remember when I was doing research for alchemy, something called sulfite mercury, sulfite salt, and sulfite lead, I believe. And if you mix all three of them together, you could possibly make a philosopher's stone. It's just, they're impossible. Where
Well, if you're, let's say you're looking for the elixir of life, what evidence do you have in support and where do you look? But, this is the difference, I think, between the alchemist and the scientist. If you read, if you watch David Sinclair, he has a bunch of YouTube videos and other things, his own channel, etc. You watch this and you go, oh, there's some evidence in support of, he's talking about, if you could reverse aging, 1 year at a time and then just continue to do this year after year, then, what is your potential lifespan?
Yeah.
And so then you're going, well, and then, well, what evidence? Is this just conjecture or what is this? And then you start reading about, what observations led him to hypothesize this, and then he came up with the theory of aging, And so it's a very interesting book. So if you're interested in Elixir of Life, read this because this will be more compelling than the early alchemists. And yeah.
Professor, I had one question about the name that you said about after alchemy, right? And we started getting into observation. What was the name?
The name of the scientific method. That's
Galileo's.
yeah. Basically, the scientific method was the turning point where things were. Because, for example, Lavoisier, he didn't hypothesize anything. He just took observations. And these are just experimental.
Was it Lavoisier?
That's a good question.
Just
I
speak
don't-
it into your phone and hope
I
it
don't know how
knows
to.
what you're saying.
I would love to, but it would make noise. I wouldn't want to.
Well,
It's like Levousier.
yeah.
Lavoisier.
Is he discussed in our book, right?
Let's say that sounds like something that we discussed in the book.
Yeah, this in the book. Our book begins with the scientific method here.
Is his first name?
Yeah.
Okay, I found it. Here you go.
Oh, thank you.
Antoine Lavoisier.
Yeah,
Assuming was,
I think he's in our book as
some
well,
sort.
but he's in the
I
Chem
can
4
see.
book.
A French scientist?
You can see the French in the OISER.
Meaning the
IER.
last, mostly the last name.
All right.
is French.
Yeah.
Those days. So it's like this whole thing. I mean, the way science is supposed to work, and this is, maybe prior to those times. Although when things can get mixed up, there's things like, for example, if you have two competing hypotheses. Even for COVID, there were two competing hypotheses, like, the origin of COVID. And the two competing hypotheses were, one, it's natural, the other, it's laboratory born,
Or mutation.
or something.
That'd be natural.
But what you want is both sides can argue their point, and both sides can present, and they're, and that's the way it should work, and that's typically how science works. Is you propose some hypotheses, but you want to see what observations led to that hypothesis. What we want. And so you'd look at it and then you'd evaluate it for yourself and see which is more compelling as far as arguments go for that. But I just, I think back to Dalton, how hard must have been to convince people of the existence of atoms, just arguing about the law of constant composition and the conservation of mass. It must have been quite difficult, I would think, because people must have lambasted him, basically, I would think.
I imagine it could have been as difficult as like someone in the past trying to convince people that the
That
world.
was round.
Yep.
That's exactly what I was thinking.
Or better yet, you could take it in modern times and people trying to convince people that the Earth is flat. It's just as difficult. There's a lot of proof proven
I
otherwise.
think in ancient Greece, there's just like a majority of people just didn't care or had no intelligence to like acknowledge, like to know about that the Earth was round.
Yeah.
It's like, it doesn't affect.
Yeah, it doesn't.
Like, if you never go that far, you'll never know.
Yeah, exactly.
Who cares?
All the intelligence was held up really to like
Okay.
top 1%, right?
Well, let's move on to this thing. Yeah. So
And have like
the nomenclature is pretty much review, right? You say. Maybe the only difference is something you might have learned thiosulfate, and the thiosulfate is important. This is a common what we call reducing agent. It's electron rich. Electron rich things are reducers and or fuels. And so we have the ides. A lot of the ides are simple off the periodic table. Some you have to memorize. So we already talked about that. And then we have the acids. You know the acids. We have the ate, the ite, and the ide. And this is the anion. I think I left off with this, and this is the acid name. And so if we end in ate, it's an ic acid. If we end in ite, it's an aus acid. And if we end in ide, it's a hydroic acid. And so the other thing is for nomenclature is something that we didn't quite have before, and that would be organic nomenclature. So let's take a look at some organic nomenclature here. And for organic nomenclature, we aren't going to be dealing with too many organics, but there are some that are quite common. That we should know. And so the simple hydrocarbons we should know here. And so let's take a look at the simple hydrocarbons here. So if we have one carbon, it gets the meth, that's the parent. If we have two carbons, the parent is F. 3 carbons, prop. And so methane. Ane means it's a hydrocarbon with all single bonds. Ene means we have a double bond. Ine means there's a triple bond. And so we can look at some simple ones here. Methane, ethane, propane. Natural gas consists mainly of methane and a little bit of ethane, and then there's some odorant put in. Methane and ethane are odorless, colorless gases. They're pretty unreactive. I mean, methane's not a very good acid, even though it has a lot of hydrogens. The reason is this bond is not very polar. You need quite a polar bond. So whenever we have an acid, the hydrogen is usually bonded to the most electronegative element. The most electronegative element here is just carbon. And carbon and hydrogen are about a tie. Carbon has electronegativity of 2.5, hydrogen 2.1. And the electronegativity difference is very small. Not only that, this is tetrahedral, so even if there were bond dipoles, they cancel out in 3 dimensions. And this is nonpolar. All these are nonpolar. So, nonpolar things don't like polar things like water. And so none of these are very soluble in water. They'll just bubble out. And as far as acid-base reactivities, these aren't very acidic at all. You could get these to react if you had what you call a superbase. So if you look at the acid chart, I'm going to hand out an acid chart later. If you have a super base, you could pluck this off. There's super bases and super acids.
I was going to ask, could I have an example of a super base? Like the formula or what
Well, one example of a super base would be amide. Have you ever heard of amide?
How do you spell it?
Yeah.
A-M-I-D?
A-M-I-D-E. Amide. Amide is special. If you take a look at this chart here, you see on the bottom right side of the chart was the most powerful base on the chart. The most powerful base is NH2-. NH2- is called amide. Amide, I used to use this stuff quite a lot, but I made it an even more powerful base. The base that I made, which was like a super base, was I take ammonia. Ammonia is normally a gas, and then you liquefy the ammonia. And then you dissolve sodium. Sodium metal dissolves in ammonia. And what happens is this, when the sodium metal dissolves in ammonia, it frees up the electron. And so it's like a solution of electrons. And it makes it a super base. Let me see if there's a picture of it, because it forms a beautiful blue solution.
Is hydrochloric an example of a superacid?
No.
No. What would be a superacid?
Like fluoroantimonic acid. You know, the superacids and superbases, there's a history in Southern California for superacids and superbases. At USC, there was a professor there named George Olah, and he won the Nobel Prize in Chemistry for his work on superacids and bases. Actually, when I was looking at graduate schools, I went to USC and went to visit his group there. What they use it for is they at the time they were looking at making synthetic gasoline, using superacids and superbases. So if you get something unreactive, well, methane is very reactive. It's quite explosive, but in other ways it's very unreactive. It doesn't react with bases, normal bases, and it doesn't react in other types of reactions. But if you can get it to react, using superacids and superbases, then what you can do is you can make more complex hydrocarbons. You can make more complex hydrocarbons than you can make gasoline. And so that's what they're looking at. And so liquid. And these are called solvated electrons. And so let's take a look at some images for solvated electrons. We have some nice images here.
That's a very deep blue.
It's a very deep, you have to get it very cold, because this is ammonia that's been liquefied, and then there's sodium, and this is just deep blue. It's pretty interesting stuff. But this you don't want to drop anything in here because it could explode. It's very reactive. Depends on what you put in there. What do they do? Okay, metallic solution. This is Science magazine. What does this say? Metallic, yeah. This is going to conduct electricity very well. So I guess that's why they call it metallic solution.
It reminds me of a process that I saw where you can take a bath of iron, I don't know what, but something, right? And you can put metal inside of it, right? And it will turn that color of that metal. And then if you place something in it and ground it, and then put the metal you would like to coat it with, and put a negative on it, you can coat that material in, say, copper or nickel.
Oh yeah. That's electroplating.
Yes.
Let's talk about Chem 1B. But these are called aliphatic hydrocarbons. Aliphatic are different than aromatic. This is called an aromatic. Aromatics have alternating single, double, single, double, single, double. When you have that, there's special things that happen with the orbitals that are involved, and we get something called delocalization versus localization. We'll talk more about that later in bonding. So, benzene's very important. This is a very common solvent. The benzene was banned for many years because they're worried about the risk of its carcinogens. So it was totally banned. But benzene was an incredibly useful solvent. This is quite nonpolar. And the degree of the risk, it turned out to be not as severe as what people were thinking, because this flat thing can, I guess, get incorporated in a groove of DNA or something, cause mutations. But now the ban has been lifted and people use it. But there was a scare. Did you hear about Perrier water?
No.
There was a scare that there was too much benzene in Perrier water. Do you know what's in Perrier water?
No, actually.
Yeah, nobody. Unless you analyze it, right?
That's not something I drink very often, no?
Wait, let's I literally had one yesterday. So I was
Yeah,
like,
right.
oops.
right. No, I don't think you have to worry now. I don't know
really
what
like
the
them.
source of benzene was, but there was a scare for benzene.
That reminds me of like a
Interesting.
meme from Alex Jones.
But benzene is a important organic, and we're going to be looking at benzene compounds. But so here they're talking about isomers. We talked about isomers before. What are isomers?
They have the same position but different structure.
Yeah, same formula, different structure. And so when we look at these, the way organic, this CH3, we give it a name. Do you know what CH3 is called?
Methyl.
Methyl. And so this one, actually, this carbon has 3 methyl groups attached to it. And then these CH2s are methylene. Methyls are the end of a chain. So the end of the chain, methyl. End of a chain, methyl. End of a chain, methyl. Methylene groups are in the middle of a chain. So we see that. And then we have a branch here, a 3-way branch, where we have 3 carbons and a hydrogen. And so they're asking, are these isomers? Well, what we have to do is they're going to have different structures, because over here we have this carbon with 3 methyl groups. Over here we have carbon with just 2 methyl groups. And then over here, this carbon doesn't have any methyl groups on it. And so it's a bit different if we were to draw it out. We just look, how many total carbon atoms, how many total hydrogens, and how many, actually that's it. So 1, 2, 3, 4, 5, 6, 7, 8. 8 carbons. 1, 2, 3, 4, 5, 6, 7, 8. 8 carbons, and then you sum up the hydrogens, and it turns out these are isomers. Here you can see organic compounds can form branches like this. We aren't going to get into naming these, but let me just quickly tell you how we name something like this. But you don't have to know this for the test or anything. Well, first we find the longest chain of carbon atoms. What is the longest chain of carbon atoms in B? The top 1, 2, 3, 4, or the bottom 1, 2, 3?
Top 4.
The top 4?
It has 4.
Okay, this is a common trick in
This is a
organic
trick
chemistry.
question.
Yeah, neither.
Okay.
Neither of those. The longest chain is 1, 2, 3, 4, 5. It doesn't
So
matter.
as long as they're connected.
Yeah, as long as they're connected, it doesn't matter. So the longest chain is 5, which means the parent is called pen. And so then we number the carbons. This would be carbon 1, this would be carbon 2. And on carbon 2 we have something called, this is a methyl, CH2CH3 is called an ethyl. So this would be called 2-ethyl pentane. That's how we'd name it. Over here, what's the longest chain?
The
5.
1, 2.
Yeah, 1, 2, 3, 4, and then we could go either up or down, doesn't matter. 5. And what do we have on this carbon and this carbon? Methyl. So this would be called carbon 2, 3, 4. Carbon 2 and 4 have a methyl. So this would be 2, 4 dimethyl, 1, 2, 3, 4, 5 pentane. Yeah. And so we have different ways of naming this. This is called a cyclo, and it depends on how many carbon atoms are in the ring. So 1, 2, 3, 4, 5. 5 carbons in the ring, which is what? Pentane. But since it's in a ring, we call it cyclopentane. So this would be a 1, 2, 3, 1, 3 dimethyl cyclopentane. That's how we name it. So this is a cyclobutane here, and then this is given a name too. Do you know what we call this little fishtail? This is CH3CH, CH3. These are called substituents. Methyl substituent, ethyl substituent. You know, this substituent is called a isopropyl. Isopropyl has 3 and it's attached to the middle. Whereas we could have an N-propyl. An N-propyl would be 3 attached to the end. And so the incorrect name for this one would be this. It would be 2N-propyl butane, or 2-propyl butane. That would be incorrect, but you could see. And so we have different substituents. Now this one is going to be 1, 2, 3, 4, so it's a but it's not going to be a butane, it's going to be a butene. And we have to indicate where the double bond is. The double bond between carbon 1 and 2 or 2 and 3? Well, it's between 2 and 3, so we call it 2-butene, indicating that the double bond starts on the second carbon. Now, the way we number these is we try to get the smallest number. So here, if I did this, I could call it 1, 2, 3, 4. This could be 4-ethyl pentane. No, because it would be better to name this 2-ethyl pentane. And so we try to go for the smallest number. Now, these are not isomers here, but this is what we call cis-butene. Cis is on the same side, the two carbons. Trans would have them on opposite sides here. And so we have those types of things. It makes a difference. You've heard of trans fats? Yeah, versus, although they don't call them cis fats, but trans fats have them on opposite sides. When they're on opposite sides, it makes the chain lay flatter, rather than if they're on the same side, it puts a kink. So what do you call it? Well, trans fats versus cis fats. Trans fats are typically solids because of how flat the fatty acids are, versus cis fats, which are typically liquids. All right, so we had different substituents here. So remember the isopropyl? Isopropyl is this propane with something stuck on the center. So this is why we call it isopropyl alcohol. It's an alcohol stuck to an isopropyl substituent, isopropyl alcohol. This is just called propyl alcohol because it's a propyl group attached to an alcohol, which is OH. And so alcohols are the next important group, which would be COH, like this. And you should know some of the simple alcohols. Simple alcohols would be methyl alcohol, a methyl, CH3, attached to an alcohol, OH, methyl alcohol, or methanol, methane-based alcohol. We have ethanol. I don't know why they didn't put ethanol here. Oh, there it is. They put ethanol at the top because ethanol is probably the most common you're familiar with. This is grain alcohol or sugar alcohol. Methanol is also called wood alcohol. There are a surprising number of deaths every year from methanol poisoning. Even Australia, 2013, 3 people died and 1 suffered partial blindness when they ingested a homemade beverage containing methanol.
No, that's Australia.
You gotta.
Australia.
Homemade.
Homemade
Do they not
beverage.
know it's
The land
Did they try to make moonshine and ended up with ethanol?
Right. Slovakia, 38 people in the
Wait.
Czech Republic.
Shit too.
Be careful if you're traveling to
Ethyl
Eastern
alcohol?
Europe. If you're traveling to Eastern Europe, this is quite common. Methanol thing. 38 people. They have El Salvador, 122 people died in 2000. Drinking low-quality liquors sold in unauthorized shops, adulterated with methanol.
You see, this is why we're not allowed to make and sell our own moonshine.
Wait, the alcohol
Estonia.
we drink is ethanol. Right?
Yeah, I made
That's
my
what I
own. You
So they're
gotta
just using
be a
the
competent
wrong thing.
chemist, that's all. You actually
Most
don't even
people
need to be a
aren't.
competent
Don't
chemist.
ingest-
So you just need to use ethanol instead of methanol, and you should be
A lot
fine.
of deaths in
Exactly.
India.
As long as you don't
Yeah,
drink
India,
100%.
Most
Wow.
deaths.
a lot of deaths in India.
Wow,
2022 when the Gujarat
How
toxic
many deaths
liquor
in like
deaths.
prohibition American case of methanol
Is that
poisoning?
2022? No,
2022.
Indonesia.
During pandemic.
Wow, wait, a mass poisoning?
Mexico.
Mexico, 35 people in 2020. That's not so long
I
ago.
expect-
Morocco was 28th and 29th of 2022 at 19 deaths.
200 people in Madagascar just
Yeah.
died.
Russia.
Yeah, at least some of the
18.
Spain is Gucci. They figured it out a long time ago.
1960.
1963.
Wow, 51 died. You know, and that
That's so many.
a lot of people say, oh, it's an urban legend that you can go blind. Well, you can go blind. Yeah,
35 people
from
dead in Russia.
9 people lost their sight.
Mm-hmm.
What, 30? What did you say?
35 people dead in Russia in 2021.
Oh, 2021. Wow.
Wow. Well, Russia.
Yeah, United States. Here we go.
80 people.
So many.
From 2010.
Yeah, Massachusetts man
2018?
died.
Why was there going to be more from our
A
country?
single man died from
The
just
product consumed was labeled as ethanol extraction, 95% ethanol, 5% water.
This
You
is
can
what
buy
I-
this in Las Vegas. You know,
Yeah.
95, 180 proof.
Yeah.
But you gotta wonder, you know, now, you want to drink it? I don't know. But I guess this was over the internet and shipped by the U.S. Postal Service.
Well, it was mislabeled then, wasn't it? Because it said it was ethanol, but it said
Yeah.
it was methanol.
It was ethanol. So you know what, hand sanitizers?
USPS.
Some hand sanitizers contain high levels of methanol,
Mm-hmm.
and so FDA pulled those.
Mm-hmm.
But I don't know if they got all of them. But yeah, you don't want hand sanitizer with methanol in there. Although they use methanol for the little sterno heaters for catering events. You know,
Mm-hmm.
methanol there. It burns nice and clean. Well, anyway, it's wood is cheap to ferment, and so this is why there's so many. But it still continues. So you gotta watch out. And then there was that incidents in the Bahamas or someplace where a couple of Americans died after going to the bar. Did you hear about that? The big mystery. But then I started to hypothesize. I wouldn't call it really a theory, but my hypothesis was that it could have been contaminated or laced with methanol. Oh, 54.
What?
But-
Drinking white windshield washer fluid?
That's an interesting drink.
Oh, interesting.
But the only difference is one carbon.
Mm-hmm.
And would you drink propanol?
No.
No. Propanol, you can't really buy it so easily, but you can buy isopropyl alcohol easily because it goes by another name. What is it?
Rubbing alcohol.
Rubbing alcohol.
Rubbing alcohol.
So, yeah.
It was so hard to find in the pandemic.
Oh, was it?
It
Oh,
was.
yeah.
Okay.
Any kind of like.
Oh, any kind of alcohol.
Yeah,
Right.
pretty much.
People were
Right.
buying it out to make hand sanitizer.
Yeah, exactly. Yeah.
Right. Well, my preference is hand sanitizer with ethanol. I like the smell of that.
Oh yeah,
better.
my mom had gotten since my mother's a nurse, she had gotten a large jug of isopropyl, right?
Uh-huh.
That was like 98% purity at medical grade.
Now I'm curious what's in my hands.
All right. How about butanol? What would butanol look like?
It would have 4 carbons
More carbons?
and another.
And then an OH. Now, alcohols are very interesting because on the one hand, alcohols look like water. On the other hand, alcohols look like hydrocarbons. And so if you look at this kind of looks like butane. And if you look over here, it looks like water. And so the solubility of these things are very interesting. Methanol is what we call miscible in water. What does miscible mean?
It can be placed infinitely and not get saturated.
Yeah, and so both of them, we'll take a composite. It's infinitely soluble. It infinitely dissolves in water. And so methanol and water are very similar. And you would think ethanol may be less soluble because we're starting to get this hydrocarbon. The hydrocarbons don't like water. It's like oil and water, right? But ethanol is also miscible. And when we get to propanol and isopropyl, that's okay. But butanol, it's hard to get this in water. You really aren't going to get much in water. In fact, this is more insoluble in water than soluble in water. And that's because of this big hydrocarbon group on the end. Okay, those are the alcohols. And then we're going to look at some other common ones, which would be the carboxylic acids.
Acetic.
Well, the carboxylic acids look like alcohols, but they have this double bond O here, and we call this the COOH group. The COOH is the carboxyl group. And we call it COOH. It looks as if there are two oxygens bonded to one another, but they aren't. You know, the two oxygens are bonded separately to carbon. And then creates this. These are called functional groups in organic chemistry. And the acidic hydrogen, which of these hydrogens is acidic? And ethanoic acid. Ethanoic acid is two carbons here. Which are acidic?
Wait, can you repeat the question?
Okay,
Acetic.
we have 4 hydrogens here. Are they all acidic?
No.
No. Which are acidic?
The left side.
The left ones?
Yes.
How come?
Because on the right side you have a base with OH.
No, this is not a hydroxide.
Oh.
Hydroxide, you have to have a metal,
Mm-hmm.
and the oxygen can take it. Now we're in a tug of war between carbon and oxygen. Oxygen can't take it, the electron, to form hydroxide. So this is not hydroxide, this is a covalently bond. This is where ionically bonded, then it would be a base. It's not a base. This is actually, it turns out to be an acid. This is the acidic hydrogen here. These 3 hydrogens are non-acidic. This is like methane. You know, you need a super base to pluck these hydrogens off. They aren't going to come off. Whereas the other hydrogens are. Do you recognize this acid here?
Yeah, acetic acid.
Acetic acid. So this is called ethanoic or acetic acid. This is methanoic or formic acid. This is the just generic carboxyl group here. What type of compound is each of the following? So A. A is a hydrocarbon. Name it. Butane. Okay. There are no double bonds here. We could draw out the Lewis structure to see that there are no double bonds, but when we have these methyl and methylene, excuse me, and methyl groups, methyl and methylene groups, and that's it. How about this one? This is a substituted hydrocarbon, and this chlorine's there, and this is not ionically bonded, this is covalently bonded. So what we call this is butane. You see it's butane because it's 1, 2, 3, 4 carbons, and the chlorine. The chlorine's on carbon 2 because it has 1 less hydrogen. You see that this is typical methylene. And so this would be called 2-chlorobutane. Chloro is the name we give halogen, chlorobromoiodo as substituent. Do you recognize this one? This is called a This is the COOH group. COOH group tells you it's a carboxylic acid. Can you name this carboxylic acid?
Acetic.
This is not acetic. Acetic is ethanoic. It has 2 carbons. How many carbons does this one have? 3. So 3 is what? Yeah, prop. And this is going to be called propanoic acid. Propanoic acid. If this were an alcohol, it would be propyl alcohol, but this is not a propyl substituent here. Okay, what type of compound is D? D is an alcohol. And the alcohol goes on this carbon here. Can you see? Because look at the hydrogen count. So it's got to be on this carbon. And how many carbons are on this chain? 1, 2, 3, 4, 5. So it's pent. There are no double bonds here. Typically they'd show the double bonds in here. And so this is pentanol. But we got to tell what carbon the alcohol is on, and what carbon is it on?
3.
Carbon 1, 2, 3. Yeah. So this would be 3-pentanol.
3 pencil.
Yeah. The trick is, if you go backwards, is it still 3 or is it a lower number? So if we go backwards, 1, 2, 3, it's the same. You know, sometimes it's lower, and they try to trick you. If the lower number is preferred, right?
Okay.
So if you had a choice between 2 and 3, 2 is the preferred. In fact, nobody's gonna call it 3. That's the choice. These are called chloro, they have classes of compounds like chlorofluorocarbon. This is chloro. But again, types. Take a look. So, A, alcohol. And how many carbons? 3, so prop. So it's a propanol. And so there are 2 ways of naming this. This could be named 2-propanol because the alcohol goes on the second carbon, or it could be named isopropyl because if you have a propane, something's attached to the middle, we call it isopropyl. And so this is isopropyl alcohol here. How about this one? This one's mixed because we see a COOH over here and we see an alcohol here. So what do you think takes precedence, the carboxylic acid or the alcohol? Carboxylic acid. And so this would be a 1, 2, 3, 4. 4 is butanoic acid, and then we have a this is when OH is a substituent, we call it hydroxyl. And so we named this based on the major, which was the carboxylic acid. So this is carbon 1, 2, 3. This would be 3-hydroxylbutanoic acid. You don't have to do anything that complicated. You just need to know the very basic ones. Knowing that, what is this one? This is a chloro and a carboxyl. Those are the 2 functional groups, chloro and carboxyl. Which one do you think is carboxyl? So this is a carboxylic acid. How many carbons? 1, 2, 3 carbons. So it's propanoic acid. Propanoic acid, but it has a chloro on which carbon? The N one. Is that carbon 1 or carbon 3? If we're calling this a carboxylic acid, then we're going to name it carbon 1 over here because and so this would actually be a 3. This would be a 3-chloro propanoic acid. Over here, this is just a halogenated hydrocarbon, right? Halocarbon, whatever you want to call it, and has a bromo group on it. Is that bromo on carbon 1 or carbon 3? Carbon 1. So this would be 1 bromo. What? Propane. Propane. Or is it propane? Because look at that, CH. Usually we have the CH2s there. So if we have a bromine bonded to the carbon, this carbon has a hydrogen here, this carbon's going to be bonded to another carbon which has a hydrogen here, and then this is going to be bonded to a CH3. Do we have enough for octets? No, we don't. And so there's actually double bonds
So it's gonna be
here.
an ene.
Yeah, it's going to be a double bond here. And so it's a propene, right? And so this is a 1 bromo, 1 propene. But that's getting more complicated than we need to get. What we should be able to do is maybe name these guys here. And so these are just what types,
Why does a carbonic acid take
Carboxylic acid?
Yeah, carboxylic.
Carbonic acid is, do you know the formula for carbonic acid? Carbonic acid comes from what anion? 8. And so what's the formula for carbonate? CO3 2 minus. So carbonic acid is this, H2CO3. Now organic and inorganic, sometimes they make simple distinctions, and sometimes these distinctions are just historical. Is carbonic acid a organic or an inorganic?
I think organic.
You'd think organic, but people call it inorganic. Well, that's a good question. Why? Um, It kind of looks like a carboxylic acid mirrored. Okay. So it's just historically known as just inorganic because carbonic acid is often associated with this. Carbonic acid is unstable. What does it decompose into?
CO2.
H2O and
CO2.
CO2. When we think of CO2, do we think organic or inorganic?
Inorganic.
Yeah, most people associate CO2 with inorganic, so this could be the reason why carbonic is often associated as an inorganic, but the distinction is most carbon-containing compounds are organic, but not all of them. These carbon-containing compounds are considered inorganic.
So it's called a carboxylic, right?
Yeah, carboxylic acid, right.
Carboxylic.
Yeah.
Okay, so why does it take precedent over the alcohol?
There's a certain ranking that goes on, so don't worry about it. You just memorize it. It's convention. People just, some things have a logical reason, others don't. But in terms of reactivity, that's the reason why. If you knew that the carboxylic acid is much more reactive than, let's say, an alcohol is. Alcohols aren't that reactive with a lot of things. We should be able to name these. Name A.
Pentane.
Pentane, good. B.
Fluorobutane?
Fluorobutane. But where does the fluoro go? What carbon number?
Two.
Yeah. So we call 2 hyphen. This is what we do. 2 hyphen fluoro. It's all one word. And was it 4 carbons?
Yeah.
Butane. So 2 hyphen fluorobutane. C.
Ethanoic acid?
Ethanoic would have how many carbons?
2.
2. So you have an ethyl group attached to the carboxyl group, but altogether they have how many carbon atoms? 3. So we're going to call it propanoic acid.
Propanoic acid.
Yeah, this one will be propanoic acid. Ethanoic acid has another name, acetic acid. How about D?
There's an
Pentane.
oh, yeah, pentanol alcohol.
1, 2, 3, 4, 5. Yeah, pentanol.
Pentanol.
Yeah,
That's 3 pentanol.
3 pentanol.
Isopentanol.
Yeah, I suppose you could use iso because it's stuck right in the middle, but people don't call it isopentanol.
Mr. Chevelle,
Mhm.
would it be right to say pentanol alcohol? for
No.
D?
When you say pentanol, that's it. Now,
Is it pentanol?
we call it 3 pentanol, right? But sometimes things get more complex when there are other things there. If I say 3 pentanol, everybody would know what you're talking about. But when we have other substituents on there, then we have to number each substituent. And so in this case, the alcohol, the OL, belongs to carbon 3. And there could be other things in there. So pretty soon we have to subdivide it into this type of system here. Okay, give plausible names for these molecules. Let's say the green is what? Typically green is
Chlorine?
chlorine. Yeah. And so if this is a chlorine, what would you name this?
Chloropropane.
3 what was it? 2 chloropropane.
That's what I meant, yeah.
Okay, 2 chloropropane. That's correct. What about this?
The first and the fourth.
Yeah, the first and the fourth. When that happens, what we do is we do this. We do, let's say, 1, 4. 1,4 hyphen.
So it'd be
It's
one.
four, so it's butane.
Hmm?
1,4,4 butane.
Okay. Are they both the same? Yeah. Okay. If they're both the same, then we use the di prefix. Di, chloro, and then how many carbons? 4? Butane. 1,4 dichlorobutane. The hyphen there. How about C? Well, do you recognize this? COOH?
Propanoic.
Yeah, propanoic acid. Except there's this thing stuck on here. What is this called? CH3. CH3 is called a. It's methane if it's CH4. CH3 is called a methyl because it's a what we call a substituent. It's missing something. And so the methyl is going to attach to which carbon? The second. And we number it from here. 1, 2. So this is 2-methyl propanoic acid. Does that make sense? Yeah. Okay. 2-methyl propanoic acid. All right. Did I do the combustion analysis?
Yes, it's last time.
All right.
To some degree.
Did we do a?
Yes, oxidizer and fuel.
Oh, yes.
Did we do a
Just
problem
oxidizer.
with combustion analysis?
I don't think so, not yet.
Okay. Well, let me talk about chapter 4 a little bit, and then we'll come back to the combustion analysis. Chapter 4 deals with chemical reactions. So combustion is the type of chemical reaction. Chemical reactions and chemical equations. Normally, we want to write a balanced chemical equation. Chemical equations and stoichiometry, we can do quantity. Stoichiometry is quantity relationships. Chemical reactions in solution, so we have aqueous reactions. And then this is just some stoichiometry. Limiting reagent, excess reagent, theoretical yield, actual yield. Other practical matters in stoichiometry. Extent of reaction. Extent of reaction would be percent yield. Those are the topics. So just some chemical reaction type stuff. And so let's take a look at this. What types of chemical reactions are there?
Physical, chemical.
Well, physical changes wouldn't be considered a chemical reaction. In a chemical reaction, you could have a color change. Color change could be physical, or it could be chemical. So this is difficult sometimes to determine.
Then
Formation of
a solid.
precipitate.
Yeah, formation of a gas and with exo endothermic reaction.
Yeah, these are typical observations in chemical reactions, but some of these could be in physical processes as well. You know, precipitate like in rain, or precipitate as in something called chemical vapor deposition. That's type of stuff. But what happens in a chemical process is that this is definitely, is that physical or chemical?
Chemical.
This is chemical. This is copper and nitric acid. This is definitely chemical here.
Is that just? Oh, that's steel wool. I thought that was magnesium.
No, it's steel wool. And so we need the balanced chemical equation, like this. This is all familiar ground, correct? Familiar stuff. Okay. This is an interesting compound here. Glycol. Glycols are polyalcohols.
What do you mean by polyalcohol? Like, with glycol?
The poly just means more than one alcohol group.
It has to be separated by something.
Yeah, like ethylene glycol. Ethylene glycol, which is used in antifreeze, has an alcohol group on one carbon and an alcohol group on another carbon.
I hear glycol, I immediately associate it with diesel.
is glycerin. Have you heard of glycerin? Is a trialcohol. It's common. And so basically in combustion analysis, we need something that burns. So we can burn this. And when we burn it, we combust it with oxygen and it forms CO2 and water. So we can work backwards from the CO2. From the CO2, we can figure out how much carbon we have. From the water, we can figure out how much what we have. Hydrogen we have. Now the oxygen gets mixed up because if you look at the oxygen, there are two sources of oxygen in our final products here. One is from the compound itself, the other source is from the oxygen we use for combustion. So we lose track of the oxygen. But if we know that this compound contains carbon, hydrogen, and oxygen, then we can figure out how much carbon, how much hydrogen, and the balance must be oxygen. And so, figure that out. That's what we do in typical combustion analysis. So combustion analysis is stoichiometry. So we'll look at some stoichiometry. Reaction conditions, some of these reactions, are you familiar with these symbols here? Delta.
Yes.
What does delta mean?
Change.
Change, but in a chemical reaction like this, it doesn't mean change. It means
Energy.
heat.
Yeah.
But you know, how much heat? Just a little or a lot? It's not, it's very qualitative. And so this is much better because this tells us how hot to heat this up, 350. And look at the pressure, 340 atmospheres. And what are these? These things are typically catalysts that help speed it up. And so these aren't reactants nor products, just other things that are added in there. And so a lot of these reactions, in fact, I saw an interesting story, interesting article in CNE News that there's some startup that just got like, I think $5 million or $20 million. And they're looking at new materials for like solar or there are a couple of things they were looking for. One was for solar, the other was for battery. And so I think this one's for battery.
We can evolve from lithium.
And the great thing is, if you want the perfect material for your battery, it would be nice to be able to develop it theoretically, right? But, you know, is the theory easy to do those types of, no, the theory is very difficult. And so there's a two-pronged approach in scientific research. One, yes, you want to use theory, but on the other hand, it's too difficult. And so they're doing targeted experiments. And so they kind of have an idea of what they want, but they need to test it. And so what they have are this reactor that can do like thousands of different formulations, you know, and some of these they can do them all at the same time. They can analyze it. So they're looking at which one produces the most hydrogen for, let's say, hydrogen production from solar energy. And they can, the way I visualize it is which one of those little dots produces the most bubbles, you know, of hydrogen gas, and then that's probably the best formulation for that. But a lot of this is just purely experimental, you know. So what I imagine they did was they probably went to 340. 340 was working okay. Maybe they went to 360, or maybe they didn't. You don't know. Did they try any other temperatures? These are all questions that pop up when you see this kind of stuff. You know, was that optimized really? And then the pressure, 340 atmospheres, you know, how much work did they get or do in getting that pressure just right? You know? For some reactions, it is just right. Like there's one very famous reaction, the Bohr-Haber reaction. Have you heard of that one?
No.
The Bohr-Haber reaction was one, like, you know, they have these things like the 10 greatest reactions in civilization. Have you heard or watched any of those?
No.
Was one of them fire?
I hope so.
Well, yeah, one of them was the Bohr-Haber reaction. And what the Bohr-Haber reaction did is it took nitrogen, like in air. Air is what percentage nitrogen?
Like over 80 or something. It's very much nitrogen.
Is it over 80?
70.
78%? Yeah. Air is 78% nitrogen. Is that by mass or by molecules? Particles. It's by particles. It's not by mass. By mass, it's a little different. And so it's about 78% oxygen by molecules or moles. And reacted with hydrogen. Well, nitrogen is what they call a honorary inert gas. It's an honorary inert gas, or a pseudo. They call it a pseudo inert gas, because nitrogen has what we call a triple bond. And the triple bond is about 1,000 kilojoules per mole to break, and so this is extremely hard to react. And so nitrogen is very unreactive. That's why we inhale nitrogen; it doesn't do anything. That's pretty unreactive. But they were able to get nitrogen to react with hydrogen to make ammonia. And so in that case, it was optimized. They tried so many different temperatures, so many different pressures until they found the optimum. And still it wasn't that great, but it was good enough. It was good enough to make ammonia. And do you know what they did with ammonia?
Turned it into a cleaning product?
They used it as a fertilizer. And so that increased, they said that increased, like that reduced starvation by orders of magnitude, and it increased food production by orders of magnitude. So it was a huge achievement.
Professor,
Yeah.
with the combination for ammonia, do you know what they had to use in order to get it? What temperature, what atmosphere they used? No.
Yeah, roughly, but in what we do is was it high temperature or lower temperatures more favorable? Higher pressures, lower pressures, this type of stuff, and then to find the perfect mix. Then that requires a lot of experimentation to do, but I don't know the exact numbers of that, but it's an interesting thing. No, it would be nice to be able to predict these, that way you don't have to waste a lot of time trying so many different things. And so that's when I see those kind of reaction conditions, I always wonder how well optimized those were. Okay, you guys are probably pros at stoichiometry, would you say?
No.
Kind of?
No?
No.
Stoichiometry, people love stoichiometry. They love stoichiometry because, when you go to organic chemistry, this is all the math you do. Yeah, and so people love organic because the math is easier.
Learn how to do it then.
Yeah. And so if you're good at stoichiometry, then you're pretty much an expert at all the math you need to do in organic, unless you go into like
Physics?
theoretical organic chemistry.
Wait, I have a question about it. What is the difference between Chem 7A here and Chem, was it 21?
Chem 21 is nursing. Chem 7A is for science majors.
Okay.
Yeah, and you have to be careful because there are 2 tracks for nursing, 20 and 21.
I didn't
And-
have to take either of those for nursing.
Okay, well, that's because many schools don't accept those. So
Because
that's
I took nursing here and I just took Chem 4.
okay. Yeah, you have to be careful which one you take because not all schools accept it.
Okay.
Okay, so then you're good.
Interesting. Because yeah, they both
Well,
just say
Chem
OChem.
4 is supposedly harder
High school
class.
chem.
Yeah, harder class.
Oh, but I loved high school chemistry. My teacher was so funny.
Okay.
We didn't learn anything, but he was funny.
My high school chemistry teacher was pretty funny too. My high school chemistry teacher always told me, if you take some HCl and sodium hydroxide, can you drink the HCl? No. Can you drink the sodium hydroxide? No. But he said, mix them together and then you can drink the product. So, all year I was waiting for him to drink the product.
He never did?
He never did. So then I thought, man, he doesn't trust his...
His own assessment.
His own,
no,
yeah.
his
Oh,
own,
making.
yeah. Because I'd like to see that,
You should do it for us.
I
You don't trust yourself either.
no, I would do it if that would be interesting, wouldn't that? No, I
Finals
don't.
day.
It's like the person who got the phone book. He probably saw somebody do the phone book and then stop the bullet, right? But the bullet went all the way through that one particular, because different amount of gunpowder and bullets. You can't trust that everything's going to be of the same precision. So even if you test it a bunch of times, I wouldn't do it like here because then, somebody might try to, repeat the experiment like a good scientist would try to repeat the experiment. But.
I think all of the chem teachers should get together and do it for you.
And the other thing is, a lot of the chemicals, they have other things in them. They aren't pure. There are impurities in there, and it depends on how much impurity. So we buy 100% alcohol here, you know, and to prevent people from drinking our 100% alcohol, and if people could consume it, then we'd have to pay a consumption tax on our alcohol. They adulterate it with carcinogenic and mutagenic chemicals.
Really?
Yeah, you don't want to drink it.
Interesting.
Yeah. Okay, so going on here, you guys know about molarity, correct? Okay, so we could skip that. And you guys know about solution dilution. This is solution dilution. If you forget about solution dilution, we just did this.
Yeah, it's water.
But we didn't use a volumetric. We used a 500 milliliter Florence flask for the sodium hydroxide. Right? 8.3 milliliters diluted to 500 gives about 0.1 molar. So this is solution dilution. This is a visual picture of solution dilution. And then you guys know about, this is solution dilution more.
Super fast question. Will we be using STP, standard temperature and pressure?
No.
Okay.
You should know what it is, but we aren't really going to be using it.
It's
I learned STP many years ago. What is standard temperature?
273.15 Kelvin.
Yeah, 0 degrees C.
1 atmosphere.
But basically never used it. Never used it because who works at 0 degrees
I was
Celsius?
gonna say. I thought
Nobody.
standard would
Me
be like
whenever I
room
visit my
temp.
father in the winter.
Therefore, this is not a standard temperature. This is called room temperature. Room temperature, well,
Isn't it like 20?
Isn't it like 23, 24 degrees Celsius?
no. What is room temperature?
25?
25.
Oh my god.
And so people use that. I think they use that because some people work in hot labs and some people work in cool labs, so that was a compromised temperature there. Maybe that's it. Do you guys remember
25, good.
limiting reagent, excess reagent stuff?
I think I do.
Oh yeah.
Yeah.
I remember.
Okay, and so the
Let me get access reagent.
yeah, limiting and excess. How to figure out the limiting reagent? How to figure out the excess reagent?
Do the conversions and then divide by the smallest.
Helps you determine the problem.
Yeah, actual yield. Do you guys remember theoretical yield, actual yield, percent yield?
Oh,
Vaguely.
Okay,
yes.
good. Then that's pretty much this chapter here. Just a lot of review topics, except the questions. The end of the chapter questions are more difficult,
I wrote that.
as you'd expect. And so that's chapter 4 in a nutshell. But let's go back to chapter 3. We'll take a look at some problems here in chapter 3. For combustion analysis. These are just some isomers, which recognizing isomers, naming some simple ones here. But let's take a look at combustion analysis. How about that? Let's look at a let's look at a straight combustion. Have you done combustion analysis before? In Chem 4?
I'm sure we did. I just don't remember.
I
So-
think, but I'm not sure.
Pretty sure, yeah.
That was very many years ago.
Okay. We'll take a look at a straightforward combustion analysis, and then we're going to look at a difficult combustion analysis problem.
There's a combustion.
I remember
Like
combustion.
the first couple of chapters that we did touch it.
Okay, so let's take a look at this one. We can combust, like for example, if we combust carbon, hydrogen, sulfur, do you know what we form? The carbon goes to CO2. This is what we call complete combustion. The hydrogen is going to go to H2O, and the sulfur goes to SO2. This is incomplete combustion. Because in order to completely combust sulfur, what should it have gone to? SO3. And that depends on the conditions. You know, the conditions, well, you got to play around with the conditions, right? You got to play around with temperature, you got to play around with pressures, you got to play around with different conditions. And so under these particular conditions, we do not form SO3, we form SO2. You'd have to be given that. If we weren't given that, I would have assumed complete combustion. It goes all the way to SO3. This is another carbon, hydrogen, sulfur. All the carbon ends up in CO2, all the hydrogen ends up in H2O, and all the sulfur ends up in SO2. So again, we see SO2 here. This is an alcohol being combusted. Now, the alcohol is going to contain oxygen. And oxygen we lose track of because there's oxygen from the compound itself and there's oxygen from the oxidizer, O2. And so all the carbon here ends up in CO2, all the hydrogen ends up in water, and the oxygen gets mixed up. So what we do is we figure out how much carbon, how much hydrogen, and then the balance must be oxygen. And so this is going in this is telling us what it is, and then asking us to figure out how much CO2 and water should be obtained. So if I had a 1.562 gram sample of this alcohol, you know, how many grams of CO2 and how many grams of water will I have? Versus, that's the forward direction, versus the reverse direction is we're going to be given the grams of CO2 and the grams of H2O. So if we look at number 44 here, paracresol is used as a disinfectant in the manufacture of herbicides. A 0.4039 gram sample of this carbon, hydrogen, oxygen compound yields this many grams of CO2 and this many grams of water. And so this is typically a typical problem here. We're given the grams of CO2. From that, we figure out how many moles of carbon, or grams of carbon first, actually. And we're given the grams of H2O. We figure out how many grams of hydrogen. And the balance must be oxygen. So let's do 44, and then we're going to look at, I don't know if we have time, 2 minutes?
We get out at 55. It's 55 today.
Oh, is it 55? Okay.
We got 7
So I think we can finish one problem.
Speed run, yeah.
We could do 2 problems here.
Any percent
Okay, so number 44 is your typical combustion analysis problem. And so we have 0.41 or 4039 grams of CHO. And we're going to burn this. So I'm just going to write O2. I don't know how much O2 I need to burn this because I don't even know the formula, so I can't write the balanced equation. But what I do know is all the carbon in my original compound is going to end up in CO2. And all the hydrogen in my original compound is going to end up in H2O. And then I figure out how much. And so there's 1.1518 grams of CO2 and 0.2694 grams of H2O. And then I'm going to use some stoichiometry based on the formula. So if I have 1.1518 grams of CO2, then what I'm going to do is I'm going to convert it into moles of CO2. So I'll just go grams to moles. And so mole of CO2 weighs how much? Well, carbon's 1201, oxygen 16 times 2 is 32. 32 plus 12 is 44. So this is going to come out to 4401 grams of CO2 per mole of CO2. And so the grams of CO2 cancel. And then I can figure out how many moles of carbon I have. And so in this case, I have 1 mole of carbon for every 1 mole of CO2. That just comes from this formula. I have 2 moles of oxygen, 1 mole of carbon. Formula is a mole ratio. And so this tells us how many moles of CO2. Now formula is a mole ratio, but I have to do an extra step here. I have to do an extra step because I need to figure out how many grams of oxygen there were, because I lost track of the oxygen. And so normally I stop here and get the mole ratio and try to simplify it, but here I'm going to do the extra step. So I'll go ahead and stop here first and then do the extra step here. And so how many moles of carbon do I have? And so this is going to be 1.1518.
0.02617.
Okay. 0.02617.
617. And
Okay,
it's to 4 significant figures.
give me one more digit.
1.
1. Okay. Okay. The extra step I'm going to do here is I'm going to calculate how many grams And so this is 12.01 grams of carbon for every 1 mole of carbon atoms. And so take that number and times by 1201. What do you get?
0.314317.
7
Yeah.
grams of carbon. Okay, next we do the water, which is essentially the same thing. I'm going to start off with 0.2694 grams of H2O. And then 1 mole of water, H2O, oxygen 16, hydrogen is 101, 202, 1802. So this is going to be 1802 grams of H2O. That gives us moles of H2O. In this case, we have 2 moles of hydrogen for every 1 mole of H2O. That gives us moles of H. Okay, we're going to stop here, calculate how many moles of hydrogen do we have.
Give me a moment. Zero point 0.029900.
0.029940.
00.
00.
Double O.
2900.
Yeah.
Thanks. Moles of hydrogen. Okay, but we'll have to do an extra step here. And so this is going to be, I'm going to use this. I'm not going to use 101 because that would only give me 3 sig figs. I'm going to use 1.008 grams of H per mole of H. And so when I'm dealing with H alone or H2, I use 1.008 or 2.016. And so how many grams of hydrogen do I end up with here?
0.030139.
Okay, now what I'm going to do is I'm going to figure out the oxygen. So this is the carbon, this is the hydrogen. To figure out the oxygen, I'm going to take the total mass. And so for oxygen, what we do is grams of oxygen is equal to the total mass, which is 0.4039 grams of CHO, minus the grams of carbon, which is minus 0.31431 grams of carbon, minus the grams of hydrogen, which would be 0.03039 grams of hydrogen. And that's going to give me the grams of oxygen. So, so can somebody do the subtraction here?
Almost done. 0.03247.
0.03247.
Yep.
Okay, thanks. We're only allowed 4 decimal places or 3 sig figs here, so I'll subscript that. Grams of oxygen. Now what we have to do is we need the simplest mole ratio. So I have the moles of carbon. I have the moles of hydrogen. Now what I need to do is I need to get the moles of oxygen. And so I'm just going to multiply this by 1 mole of oxygen atoms weighs 16.00 grams. And that's going to give me the moles of O. So what do you get for this? Alex, this is my calculator guy.
I don't know.
But you, or somebody else.
2.029375 times 10 to the negative third, or 0.002029 or I guess 4.
375.
Moles of O. Okay, which one's the smallest?
Most of it oxygen.
Oxygen. So we're going to divide everything by this. And then we're going to get C, which will be 0.026171 divided by 0.002029. H, which would be 0.02990 divided by 0.002029. And O, 1.000. And then we will calculate it and then come up with the simplest whole number ratio. Is that okay?
Yeah.
So this is your standard dimensional analysis problem, but we're out of time. So. The other type of problem is we start off with the formula and figure out how many grams of CO2 and how many grams of H2O produced. I may change the exam a little bit since I'm behind.